All right, in 8.6, we're going to finish talking about significance tests for means. So a significance test for a population mean is often referred to as a one-sample t-test for mu, making sure you use the correct symbols. How to use the four-step process. You know this by now. The state step, you're going to state the hypothesis you want to test, and the significance level, and define any parameters that you use, so that all three parts are really important. State the test. That means that the hypothesis, the significance level, and define the parameters. If you don't have one of those steps, you'll lose points, so make sure you do all three. On the plan step, you want to identify the appropriate inference method and check the conditions. Okay, what method is it? It's the one sample t-test for mu. Okay, checking the conditions, hopefully you know that. If the conditions are met, we perform the calculations, find the sample statistic, which is going to be t, calculate the sample test statistic using your calculator, and find a p-value. Okay? Then you make a conclusion. You either reject or fail to reject the null, and you either have convincing evidence or you do not have convincing evidence of the alternative hypothesis. Now, the result of a significance test begins with the reason to reject null or fail to reject the null. When we reject the null, we're left wondering what the actual mean could be. So that's where a hypothesis test leaves us hanging. We can say, well, it's definitely not whatever the null says, but we don't know what it is. A confidence interval, however, provides the entire set of plausible values for a parameter based on the data given. So if you remember, confidence intervals gives us a range of values that it could be in. So it gives us a little bit more information. So the link between two tests and a two-sided test, remember that's when it's a not equals to or a different from two-sided test, a not equals to, and a confidence interval for a population mean allows us to make a conclusion directly from a confidence interval. So what does that mean? That means you can look at the confidence interval and know if you should reject or fail to reject automatically. If a 95% confidence interval for mu does not capture the null value, then you can reject the null at the 0.05 significance level. So notice the connection, 95% and 5% right here. All right. If, however, the 95% confidence interval for mu captures the null value, then we would fail to reject at the alpha equals 0.05 level. The same logic applies for other confidence levels, but only for two-sided tests. Okay, so I'm saying it applies to confidence intervals for proportions or means. It works the same, but regardless, it's only talking about a two-sided test. So here's example 1. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along the stream. Here are the results in milligrams per liter, and there's the 15 measurements. A mean dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do we have convincing evidence at the 10% significance level that aquatic life in the stream is at risk? All right, so we're going to state what it is. What do we want to test? We want to test at the alpha is 10%, 0.10, and our hypothesis. The null is that the mean is equal to 5 milligrams per liter, and the alternative is that we want, is it putting life at risk? And to put life at risk would be, what did it say? Below 5 milligrams, so I say less than 5 milligrams, where mu is equal to the true mean dissolved oxygen level in the stream. All right, so we've identified our test, our hypothesis. We have identified the significance level, and we've defined a parameter. Now for the plan step, there's 3 things, right? What test do we want to do? We want to use the one sample t-test. Okay, then we check our conditions. Do we know if this is random? It says 15 randomly chosen. So I say SRS, n equals 15. Now to know if this is normal, how are we going to know if this is normal? Remember there's three options. The first option is it's stated in the problem. So look at our problem. Did it tell us that our sample is random? No, it does not. So it's not going to work in option 1. Number 2, central limit theorem. Is our sample 30 or greater? No, it's only 15. So we have to go with option 3 where we graph it using a box plot or something like that. If you want to make a dot plot, you can do that. So the way we're going to prove normality is looking at the box plot. So in my calculator, I've already entered the data, and here it is. Here's what the box plot looks like. You can see it's basically symmetrical, and it has no outliers. And that's all we need to know. So I'm going to sketch the box plot on my paper. And I would make a statement that the box plot shows no skewness or outliers. So it's approximately normal. All right, that's what you got to do for the plan step. So to do the do step, we need to show our work and showing our formula, but we need our statistics to do that. We need to know, okay, X bar, we need the sample standard deviation. We know what mu is because that was used in our null hypothesis. That was 5, and we know what n is. That was 15, our sample size. So to get X bar and S, I'm going to use my calculator. I've already entered the data into the list. And what did I do? I went to stat, tests, t-test, which is number 2. I'm asking it to pull from the data in the list. I changed the null to 5. List 1 is where my information is. Frequency, leave it alone. And mu is a less than because that's what we use in the alternative. So I come down to calculate, and it's going to generate all those values for me. So X bar is 4.771, S is 0.9 or 0.3940. All right, that's enough information to write my T equation. So it goes 4.771 minus 5 over S, 0.940 over the square root of 15. And that's going to generate the T value that I need. All right, it gave me a T value of negative 0.943. Okay, so then I draw my curve. Negative 0.943 is over here on the left. And I shade because it points to the right. The alternative hypothesis points to the right. Then I need to go back to my screen and look at what is the p-value? What is the area that I've shaded? Come straight from the calculator. My p-value is 0.181. All right, from there I can make a conclusion. Now I want you to remember though, the alpha level on this problem is 0.10. This one stated a different alpha than we're used to, but that's okay. We're going to still restate how the p-value compares. So we're going to say because our p-value 0.181, that is greater than 0.10. So if it's greater than, then we fail to reject. Fail to reject the null. And if we fail to reject, we do not have evidence. So we do not have convincing evidence that the true mean dissolved oxygen level is less than 5 milligrams per liter. So make sure it has full context and reference the true mean of something. Radon is a colorless, odorless gas that is naturally released by rocks and soils and may concentrate in tightly closed houses. It is highly radioactive, so there is some concern that it may pose a health hazard. Radon detectors are sold to homeowners, but the detectors may be inaccurate. University researchers placed a random sample of 11 detectors in a chamber and exposed them to 105, I don't know what that is, per liter of radon over 3 days. A graph of the radon readings of the 11 detectors shows no strong skewness and no outliers. The 90% confidence interval for the true mean reading is between 99.61 and 100.3. So there's our confidence interval. That's the range of values it could be. What conclusion would you make if you were making a test at the alpha equals 0.10 significance level with the null that the mean is 105 and the alternative is not equal to 105, where mu is the true mean reading in the population of radon detectors? All right, so if this is our mu, this is our null, sorry, and this is our alternative, we're trying to find evidence that it's not 105. Well, look at our range of values. It's 99.61 to 110.03. Okay, so first of all, look at this. The 90% confidence interval corresponds to the alpha of 0.1. Hopefully you see why, because 0.1 is 10%. 10% plus 90% makes 100. So those two correspond together. But the real question is we're looking for evidence that the true mean value is 105. All right? So is 105 within this interval between 99.61 and 110 to 0.03? 105 is in there, so we're good to go. So the way I would finish this is say, because 105 is within the 90% confidence interval, we have convincing evidence. We would fail to reject the null. Okay? Fail to reject the null because 105 is possible. It's in there. We don't want to reject it. So our terminology is we would fail to reject the null. Then we would say we do not have convincing evidence that the true mean reading in the population of radon detectors is, what does the alternative say, different than 105 ppl, whatever that, however you say that, okay? So it's very similar to our conclusion from a hypothesis test, but we're referring not to a p-value, but we're referring to a confidence interval. All right? Hope that makes some sense, and we'll see you guys in class.